something 10 times the size of Earth is hiding in the darkness beyond Neptune, pulling invisible strings across our solar system. We know it's there because distant worlds are dancing to its gravitational tune, tilting and clustering in ways that should be impossible. We'll journey through the mathematical detective work that revealed this cosmic puppet master, explore the desperate telescope searches scanning 20,000 square degrees of empty space, and uncover why this discovery could rewrite the story of how planets form. If you're ready to hunt for the most elusive world in our solar system, hit that like button and subscribe for more cosmic mysteries. Prepare yourselves. We begin.
"4 billion miles from the Sun, something is very wrong with the outer solar system. Out in the Kuiper Belt, where chunks of ice and rock drift in the cosmic deep, 6 massive objects are behaving like cosmic rebels. These aren't your typical space rocks. Each one is bigger than a mountain, some larger than entire states, and they're all doing something that should be impossible. Picture a classroom where 6 students are sitting. Now imagine walking in to find all 6 desks turned at exactly the same weird angle, all facing the same strange direction. You'd know immediately that something made them move that way. Someone or something arranged them. That's exactly what astronomers found when they studied these distant worlds. Objects like Sedna, Biden, and the mysteriously named 2012 VP 113. Each one follows an orbit so stretched and tilted that it looks like a cosmic egg lying sideways. But here's the kicker, they're all tilted in almost exactly the same direction. The odds of this happening by chance? About the same as flipping a coin and getting heads 20 times in a row. We're talking about 1 in 64 chances. That's not coincidence. That's evidence. These objects live so far from the Sun that light takes over 6 hours to reach them. Out there, the Sun looks like just another bright star. There's no heat, no warmth, just the endless cold of deep space. Yet something is controlling their paths with invisible hands. Think of it like a shepherd herding sheep. You can't see the shepherd, but you watch the sheep all moving in formation, all responding to the same invisible commands. The sheep are these distant worlds. The shepherd is something we've never seen. What makes this even stranger is how these objects move. Most things in the solar system orbit the Sun like cars on a racetrack, staying roughly in the same flat plane. But these rebels are tilted up and away from everything else, like they're following rules written by a different cosmic authority. Scientists call this the clustering problem. When you plot these orbits on a map, they all point toward the same region of space. It's as if something massive is out there, something with enough gravitational muscle to boss around worlds the size of Texas from billions of miles away. For decades, astronomers assumed the outer solar system was mostly empty space, with a few scattered ice balls. We thought we had mapped the major players, the 4 gas giants, Pluto, and some cosmic debris. We were wrong. These orbital rebels are messengers from the dark, telling us that our solar system has been hiding a secret for 4.5 billion years. But the mystery is just beginning to unfold. 2 astronomers at Caltech stared at their computer screens and saw the impossible staring back. Mike Brown and Konstantin Batygin weren't looking for a new planet that day in January 2015. They were trying to debunk one. Another team had claimed that a massive world was lurking beyond Neptune, and Brown was determined to prove them wrong. He was, after all, the man who had helped kill Pluto's planet status. He knew how to destroy planetary dreams with cold, hard math. But the numbers wouldn't cooperate. Every calculation pointed to the same shocking conclusion. Something enormous was hiding in the darkness. Think of it like being a detective who discovers footprints at a crime scene. You can't see the person who made them, but the prints tell you everything. How heavy they were, which direction they walked, even what size shoes they wore. Brown and Batygin were cosmic detectives, and the footprints were gravitational. They fed every known orbit from the outer solar system into their computers. Objects like Sedna, with its egg-shaped path that takes 11,000 years to complete. Worlds like 2007 TG 422, which swings so far out that it practically leaves the solar system entirely. Each orbit was a clue. The computer simulations showed something that made their hearts race. If you removed everything beyond Neptune and let the solar system evolve naturally, those rebel objects should scatter randomly across the sky. Their orbits should point in every direction like spokes on a broken wheel. But they don't. They cluster together like iron filings around a hidden magnet. Brown and Badigan tried everything to make the clustering disappear. They adjusted their models, they questioned their data, they ran the simulations thousands of times with different starting conditions. The result was always the same. These distant worlds were being herded by something massive. The math demanded a world at least 10 times heavier than Earth, orbiting somewhere between 200 and 700 times farther from the Sun than we are. That's so distant that it would take this hidden giant between 10,000 and 20,000 years to complete a single orbit. Picture trying to find a black cat in a coal mine at midnight. Now imagine that coal mine is bigger than the entire United States, and you're searching with a flashlight. That's the challenge facing astronomers trying to spot Planet 9. Brown and Badigan published their findings with a confidence that shocked the scientific community. They weren't suggesting Planet 9 might exist, they were declaring it must exist. The evidence was written in the orbital language of worlds we could see, pointing toward a cosmic giant we couldn't. But proving something exists and actually finding it are two completely different battles. Imagine trying to control a marble from 3 miles away using only the power of your thoughts. That's essentially what Planet 9 is doing to objects in the outer solar system. Except the distances are measured in billions of miles, and the marbles are worlds larger than continents. This invisible puppet master is orchestrating a gravitational dance that spans distances so vast they break human comprehension. Gravity is a deceptively gentle force. Right now, you're experiencing the full gravitational pull of an entire planet, Earth, and it's just barely enough to keep your feet on the ground. A gentle jump can overcome it temporarily. Yet somehow, Planet 9 is reaching across interplanetary space to influence worlds with the precision of a cosmic choreographer. The key lies in what scientists call orbital resonance. Picture a parent pushing a child on a swing. Push at the wrong moment, and nothing happens. Push at exactly the right moment, again and again, and tiny forces build into powerful motion. Planet 9 doesn't need to be close to its targets. It just needs to be patient. Every time one of those distant objects completes its orbit around the Sun, Planet 9 gives it a tiny gravitational nudge. Just a whisper of force, barely perceptible. But over millions of years, those whispers accumulate into commands that reshape entire orbital paths. Consider the object called Sedna. It swings out to 900 times Earth's distance from the Sun, so far that the Sun appears smaller than a pinhead held at arm's length. At that distance, Sedna should be free from any planetary influence. It should wander wherever cosmic chance takes it. Instead, it follows a precise elliptical highway, as if it's riding on invisible rails. Planet 9 acts like a gravitational lighthouse, sweeping its influence across the darkness. Objects that venture into its domain get caught in what astronomers call secular resonance, a kind of long-term gravitational relationship that slowly but steadily alters their orbits. The math is both beautiful and terrifying. Planet 9's gravity doesn't need to be strong. It just needs to be persistent. Like water carving the Grand Canyon, tiny forces applied over geological time can move mountains, or in this case, worlds. But here's what makes this truly mind-bending. Planet 9 isn't just controlling these objects randomly. It's organizing them into specific patterns, creating what looks like a cosmic filing system. Objects with similar orbital characteristics get grouped together, as if they're responding to the same gravitational filing clerk. This isn't some chaotic force randomly disturbing the outer solar system. This is precision engineering on a scale that dwarfs anything humans have ever attempted. Planet 9 has been playing cosmic billiards for billions of years, and every shot has been calculated with mathematical perfection. The question that keeps astronomers awake at night is simple yet profound. What kind of world possesses this level of gravitational authority? Finding Planet 9 is like searching for a single black grain of rice scattered somewhere across the entire surface of North America. The moment Brown and Badigan published their prediction, observatories around the world began the most ambitious treasure hunt in astronomical history. Teams in Chile, Hawaii, California, and Australia pointed their most powerful telescopes toward the night sky, each hoping to claim the discovery of the century. But Planet 9 had every advantage. It's probably darker than charcoal, reflecting less than 5% of the sunlight that reaches it. The Sun, from Planet 9's perspective, appears 27 times dimmer than it does to us. That means Planet 9 receives less than 1/700th of the solar energy that Earth gets. It's essentially a frozen world drifting through permanent twilight. Picture trying to spot a black basketball floating in a swimming pool, but the pool is the size of Texas, and you're searching with a pair of binoculars from an airplane. Now make the basketball move in slow motion, and you're getting close to the challenge facing astronomers. The search zone covers 20,000 square degrees of sky. To put that in perspective, the full moon covers about half a degree. That means astronomers need to examine an area equivalent to 40,000 full moons, looking for something that might be 1,000,000 times fainter than what your naked eye can see. Modern telescopes can capture incredibly detailed images, but they see the universe one small patch at a time. The Subaru telescope in Hawaii, one of the primary Planet 9 hunters, captures an area about the size of 4 full moons in each photograph. That means it would take 10,000 individual images to cover the entire search zone just once. But here's the cruel twist: planets move. By the time you finish photographing the entire search area, Planet 9 has shifted to a new position. It's like trying to photograph every grain of sand on a beach, while someone slowly stirs the sand with a giant stick. The motion is glacially slow. Planet 9 probably moves less than 2 arc minutes per year. That's about 1/15th the width of the full moon. But when you're dealing with distances measured in billions of miles, even that tiny motion means the planet could be hiding in a completely different part of the sky than where calculations predict. Teams developed new strategies. Instead of looking for Planet 9 directly, they started looking for its motion. They would photograph the same patch of sky multiple times over several months, then use computers to identify anything that moved between images. Stars stay put. Galaxies don't move. But planets do. The computers flagged millions of moving objects. Most turned out to be asteroids, closer to home and much brighter than Planet 9 would appear. Others were cosmic rays hitting the telescope's detector, creating false signals that looked like moving points of light. Each promising candidate required weeks of follow-up observations to confirm or rule out. Teams would watch potential Planet 9 candidates for months, tracking their movements, measuring their brightness, hoping for the discovery that would rewrite astronomy textbooks. But the darkness beyond Neptune kept its secrets, and the most elusive world in our solar system remained hidden. 6 worlds, billions of miles apart, all telling the same impossible story. When astronomers first noticed that distant objects in the outer solar system were clustering together, they assumed it was a statistical fluke. Space is vast, and coincidences happen. But as more objects were discovered, the pattern became undeniable. These weren't random coincidences. This was evidence of a conspiracy. The smoking gun lies in something called the argument of perihelion. That's the technical term for the point where each object comes closest to the sun during its orbit. Think of it as the bottom of a cosmic roller coaster, the point where each world reaches maximum speed before climbing back into the outer darkness. For 6 major objects beyond Neptune, these closest approach points all cluster within about 60 degrees of each other on the sky. Picture a clock face. If one object reaches its closest point to the Sun at 12 o'clock, the others all cluster between 10 o'clock and 2 o'clock. The odds of this happening randomly are about the same as winning the lottery twice in the same week. But the conspiracy goes deeper. These objects don't just cluster in one direction, they're also tilted away from the main plane of the solar system by similar amounts. Most planets orbit the Sun like cars on a flat racetrack, staying within a few degrees of the same level. But these distant rebels are tilted upward by 15 to 30 degrees, as if they're all following the same tilted highway into space. The object called Biden provides a perfect example. It's about the size of Pluto, and it takes 550 years to complete one orbit around the Sun. At its farthest point, Biden ventures out to nearly 150 times Earth's distance from the Sun. That's so far that radio signals would take over 20 hours to reach it. Yet Biden's orbit is precisely aligned with the other conspirators. Its orbital plane, its tilt, its direction of motion, everything matches the pattern predicted by Planet 9's gravitational influence. Then there's 2012 VP 113, discovered by the same team that found Biden. This object follows an even more extreme path, swinging out to over 200 times Earth's distance from the Sun. Its orbit takes 4,000 years to complete, yet it too follows the same mysterious alignment. The most compelling evidence comes from computer simulations. When astronomers remove Planet 9 from their models and let the solar system evolve naturally, the clustering disappears within a few million years. The objects scatter randomly across the sky, following the chaotic paths you'd expect from worlds influenced only by the Sun and the known planets. But when they add Planet 9 back into the simulation, a world 10 times Earth's mass orbiting at the predicted distance, the clustering reappears like magic. The scattered objects gradually migrate into the same tilted, aligned configuration we observe today. The conspiracy extends beyond just orbital alignment. These objects also show similar colors and compositions, suggesting they might have formed in the same region of the early solar system before being scattered by Planet 9's gravitational influence. 6 witnesses, all testifying to the presence of something massive lurking in the cosmic shadows. But the mathematical evidence was about to become even more convincing. The numbers don't lie, and they're screaming that something massive is pulling the strings. When astronomers want to prove something exists, they turn to statistics, the cold, objective language of probability that strips away wishful thinking and reveals mathematical truth. In the case of Planet 9, the statistics are so compelling they border on the undeniable. The clustering of distant objects isn't just unusual, it's mathematically impossible without an external force. Imagine flipping 6 coins and having them all land heads up. That would surprise you. But it happens about once in every 64 tries. Now imagine flipping those same 6 coins 100 times in a row, and they land heads up every single time. That's not luck anymore. That's evidence of loaded coins. The orbital alignment of these distant worlds represents odds far worse than loaded coins. When astronomer Scott Shepard calculated the probability of 6 objects randomly clustering the way they do, he found chances of about 1 in 14,000. But that was just the beginning. As more objects were discovered, the evidence became overwhelming. The object called 2014 SR 339 follows the same tilted, elongated orbit as the others. So does 2013 RF 98. Each new discovery that fits the pattern makes random chance less and less believable. Think of it like finding a crime scene where 6 witnesses all give identical testimony, down to the smallest details. Either they're all lying in perfect coordination, or they're all telling the truth about something they actually witnessed. The statistical analysis goes beyond simple clustering. These objects also show what astronomers call longitude of perihelion alignment. That's the direction in space where each object makes its closest approach to the Sun. For all 6 major objects, this direction points toward the same narrow wedge of sky. But here's where the mystery gets even stranger. The objects aren't just aligned, they're anti-aligned with Planet 9's predicted orbit. They cluster on the opposite side of the solar system from where Planet 9 should be. It's as if they're running away from something, all fleeing in the same direction. Computer simulations explain this perfectly. Planet 9's gravity doesn't just attract these objects, it shepherds them into stable orbital configurations that keep them safely away from close encounters. It's like a cosmic traffic cop, directing the flow of distant worlds to prevent collisions. The math becomes even more convincing when you consider what astronomers call the Kozai mechanism. This describes how a distant massive object can gradually change the orbits of smaller objects, tilting them and stretching them into the exact configurations we observe. Planet 9's influence operates on timescales that dwarf human history. It takes millions of years for the gravitational shepherding to guide these distant objects into their current alignment. The clustering we see today is the result of patient gravitational sculpting that began when Earth was still a molten ball of rock. Recent discoveries have only strengthened the case. Objects like the Goblin and Far Out both show orbital characteristics consistent with Planet 9's influence. Each new addition to the family of distant objects provides another data point in the statistical case for a hidden ninth planet. The mathematical evidence has reached a tipping point where denying Planet 9's existence requires explaining away coincidences that strain credibility. But identifying the puppet master is only half the mystery. Understanding what kind of world could wield such power is the other half. Planet 9 isn't just hiding its location, it's hiding its identity. The gravitational evidence tells us that something massive is lurking beyond Neptune, but determining exactly what that something is requires detective work that pushes the boundaries of planetary science. Is Planet 9 a super-Earth, a rocky world built like our planet but scaled up to massive proportions? Or is it a mini-Neptune, a smaller version of the ice giants with thick atmospheres and exotic compositions? The mass calculation is relatively straightforward. To shepherd distant objects the way Planet 9 does, it must weigh at least 5 times more than Earth, and probably closer to 10 times more. That puts it squarely in the category that astronomers call super-Earths, worlds that are bigger than our planet but smaller than Neptune. But mass alone doesn't tell the whole story. A world 10 times Earth's mass could be a dense, rocky super-Earth about twice our planet's diameter. Or it could be a fluffy mini-Neptune 3 times Earth's size, filled with water, methane, and hydrogen. The difference matters because it tells us where Planet 9 came from and how it got to its current location. Think of it like trying to identify a person from their shadow. You can tell they're tall, but you can't tell if they're a basketball player or just someone wearing platform shoes. Planet 9's gravitational shadow reveals its mass, but not its composition. The rocky super-Earth scenario paints Planet 9 as a world built like Earth but scaled up dramatically. Its surface would be a frozen wasteland of rock and ice, with temperatures hovering around -400 degrees Fahrenheit. Any atmosphere would be frozen solid on the surface. This would be a world where carbon dioxide snow falls like ash from the sky, and the ground is hard enough to shatter diamond. The mini-Neptune scenario is far more exotic. This version of Planet 9 would be wrapped in a thick envelope of hydrogen and helium, perhaps with deeper layers of water and ammonia ice. Its core might be rocky, but most of its bulk would be gas and ice. This is a world where the atmosphere itself outweighs entire continents on Earth. Recent studies suggest Planet 9 is probably closer to the mini-Neptune model. Computer simulations of planetary formation show that rocky super-Earths have trouble growing beyond about 5 Earth masses in the outer solar system. There simply isn't enough solid material out there to build truly massive rocky worlds. But mini-Neptunes can grow much larger by accumulating gas directly from the solar nebula, the disk of hydrogen and helium that surrounded the young sun. If Planet 9 is indeed a mini-Neptune, it formed during the first few million years of the solar system's history, when gas was still plentiful. The size debate has profound implications for Planet 9's brightness. A rocky super-Earth would be extremely dark, reflecting less than 5% of the sunlight that reaches it. But a mini Neptune might have clouds or haze in its atmosphere that could make it slightly brighter and easier to detect. The temperature difference also matters. A rocky world loses heat slowly, staying warm for billions of years through radioactive decay. But a mini Neptune cools faster, potentially making it detectable in infrared light as it radiates away its internal heat. Understanding Planet Nine's true nature could revolutionize our knowledge of planetary formation, but first we need to solve an even bigger mystery. How did something so massive end up so far from home? Planet 9 might be an alien world that our sun stole from another star. 4.5 billion years ago, our solar system wasn't the lonely island it is today. The sun was born in a stellar nursery, a crowded neighborhood where hundreds of young stars formed from the same giant cloud of gas and dust. In that cosmic daycare center, planetary theft was not just possible, it was inevitable. Picture a cosmic game of musical chairs. But instead of chairs, stars are stealing planets from each other. Young stars in dense clusters regularly pass within a few hundred times Earth's distance from each other. That might sound far, but in cosmic terms, it's close enough for gravitational hijacking. Computer simulations of these early stellar encounters reveal something shocking. When two star systems pass close together, their outer planets get tossed around like cosmic ping-pong balls. Some planets get ejected entirely, becoming rogue worlds that drift alone through interstellar space. Others get captured by the passing star, becoming permanent members of a new stellar family. The math works perfectly for Planet 9, a world with 10 times Earth's mass. Originally orbiting another star at a distance similar to Jupiter's orbit, could be captured by our Sun during a close stellar encounter. The gravitational dance would fling it into exactly the kind of distant, tilted orbit that Planet 9 follows today. This scenario explains several mysteries that have puzzled astronomers. First, it explains why Planet 9 orbits so far from the Sun. Objects that form in our solar system should orbit closer to home, where there was more material to build from. But a captured planet could easily end up in the outer reaches where Planet 9 lurks. Second, it explains Planet 9's tilted orbit. Planets that form naturally around a star tend to orbit in the same plane, like records spinning on a turntable. But a captured planet would retain some memory of its original orbital plane around its birth star, creating the tilted path we predict for Planet 9. The rogue planet theory also explains why Planet 9 seems to be a mini Neptune rather than a rocky super-Earth. Mini Neptunes are incredibly common around other stars. They're actually the most abundant type of planet in the galaxy. Our solar system is weird for not having any mini Neptunes between Earth and Neptune. Planet 9 might be filling that gap with a world it stole from somewhere else. Think of Planet 9 as a cosmic immigrant, carrying the chemical fingerprints of another stellar system. If we ever find it and study its composition, we might discover elements and isotope ratios that don't match the rest of our solar system. It would be like finding a person with a foreign accent in your hometown, clear evidence of distant origins. The capture process wasn't gentle. Planet 9 would have been yanked away from its birth star with tremendous violence, probably losing any moons it might have had in the process. It would have tumbled through space for millions of years before settling into its current orbit around our Sun. But the rogue planet theory faces one major challenge. Capturing a planet is incredibly difficult. The gravitational dance has to be perfectly choreographed, with precise speeds and angles. Most close encounters between star systems result in planets being ejected into interstellar space, not captured. Recent studies suggest that only about 1 in 1,000 close encounters results in successful planet capture. That makes Planet 9 either incredibly lucky or evidence that the early solar system experienced more stellar encounters than we previously thought. Either way, Planet 9 might be our solar system's most exotic immigrant, a world that traveled between the stars before calling our Sun home. But there's an even stranger possibility lurking in the shadows. What if Planet 9 isn't a planet at all? While most astronomers focus their telescopes on finding a massive world beyond Neptune, a few maverick scientists are exploring possibilities that sound like science fiction. The gravitational evidence is rock solid. Something with significant mass is influencing the outer solar system, but that something might be far stranger than a conventional planet. The primordial black hole theory turns the search for Planet 9 into a hunt for one of the universe's most exotic objects. These aren't the monster black holes that swallow stars and entire solar systems. Primordial black holes are microscopic remnants from the universe's violent birth, compressed to densities that defy imagination. A primordial black hole with the mass of 10 Earths would be smaller than a bowling ball, yet it would warp spacetime exactly like Planet 9 is predicted to do. It would shepherd distant objects with the same gravitational precision, creating the same clustering patterns that convinced astronomers a ninth planet exists. The idea isn't as crazy as it sounds. Cosmologists believe primordial black holes formed during the first fraction of a second after the Big Bang, when density fluctuations in the early universe collapsed under their own gravity. These ancient relics could be scattered throughout the galaxy, invisible until their gravitational effects give them away. Finding a primordial black hole would be nearly impossible with current technology. Unlike planets, black holes don't reflect light. They don't emit heat. They're essentially invisible, except for their gravitational influence. The only way to detect one would be to notice its effects on nearby objects, exactly what we're seeing in the outer solar system. But the primordial black hole theory faces serious challenges. These objects are extremely rare, and the odds of one being captured by our solar system are astronomically small. It would be like winning the cosmic lottery with a ticket you didn't know you bought. The dark matter hypothesis offers an even more exotic explanation. What if the gravitational effects attributed to Planet 9 are actually caused by a concentration of dark matter, the mysterious substance that makes up most of the universe's mass but interacts only through gravity? Dark matter normally spreads itself thinly throughout space, invisible and undetectable except through its gravitational effects on visible matter. But under certain conditions, dark matter can clump together into dense halos that behave like massive objects. A dark matter halo with the mass of several Earths could theoretically produce the same gravitational shepherding effects as Planet 9. The appeal of the dark matter theory is that it explains why Planet 9 has been so difficult to find. Dark matter doesn't emit or reflect light, making it completely invisible to telescopes. It would be the ultimate cosmic hide-and-seek champion, something with enormous gravitational influence but zero visibility. Some scientists have proposed even more exotic alternatives. Could the gravitational anomalies be caused by modifications to Einstein's theory of gravity that only become apparent at extreme distances? Or could they result from interactions with extra dimensions that exist beyond our normal three-dimensional space? These alternative theories share one common problem: they're almost impossible to test with current technology. Unlike a conventional planet, which would eventually show up in powerful enough telescopes, primordial black holes and dark matter concentrations remain stubbornly invisible. The scientific community remains largely skeptical of these exotic alternatives, not because they're impossible, but because they require invoking rare and poorly understood phenomena to explain observations that a conventional planet explains perfectly well. But until someone actually finds Planet 9, these alternative explanations continue to lurk in the shadows of possibility. The search, meanwhile, was about to become a high-tech treasure hunt involving the most powerful telescopes on Earth. Finding Planet 9 has become the ultimate test of human ingenuity and technological precision. From the volcanic peaks of Hawaii to the bone-dry deserts of Chile, the world's most advanced telescopes have turned their electronic eyes toward the outer darkness, each hoping to capture the first photons of light reflected from our solar system's most elusive world. This isn't just astronomy anymore, it's technological warfare against the cosmic dark. The Subaru telescope on Mauna Kea leads the charge with its Hyper Supreme Cam, a camera so sensitive it could detect a candle flame on the moon. This mechanical eye captures images covering an area of sky equivalent to 9 full moons in a single shot. But even with that enormous field of view, mapping the entire Planet 9 search zone requires thousands of individual exposures. Each night of clear weather represents a precious opportunity. Telescope time is more valuable than gold, with astronomers from around the world competing for just a few hours of observation. Planet 9 hunters must balance the enormous search area against the limited time available, making strategic decisions about where to point their instruments based on the latest orbital predictions. The Dark Energy Survey Telescope in Chile takes a different approach, using a 570 megapixel camera to conduct the deepest, widest survey of the southern sky ever attempted. While its primary mission is to study dark energy and distant galaxies, the survey data contains a treasure trove of information about moving objects in our own solar system. Think of it like taking a time-lapse movie of the entire night sky. Objects that appear in multiple images but shift position between exposures are flagged as potential planets or asteroids. The challenge lies in distinguishing Planet 9, moving slowly at the edge of the solar system, from the millions of faster-moving asteroids that populate the inner solar system. The Catalina Sky Survey in Arizona has transformed itself into a Planet 9 hunting machine, using a pair of telescopes to scan nearly the entire northern sky every month. Their computers process over 1 million images per year, identifying anything that moves against the background stars. Each promising candidate triggers follow-up observations to determine whether it's a new asteroid, a known object, or possibly the discovery of the century. Modern telescope surveys generate enormous amounts of data. A single night of Planet 9 hunting can produce over a terabyte of information, enough to fill hundreds of DVDs. Supercomputers work around the clock to process these images, applying sophisticated algorithms to subtract known stars and galaxies, leaving only the moving objects that might be planets. The search strategies have evolved into an art form. Some teams focus on areas of sky where Planet 9 should appear brightest, assuming it's closer to the Sun in its orbit. Others search the opposition point, the direction directly opposite the Sun, where Planet 9 would show the most motion against background stars. Each telescope brings unique advantages to the hunt. The Large Synoptic Survey Telescope, currently under construction in Chile, will revolutionize the search when it comes online. This facility will photograph the entire visible sky every few nights, creating an unprecedented movie of the cosmos that should reveal any moving objects larger than a few hundred miles across. But despite years of intensive searching and thousands of hours of telescope time, Planet 9 continues to elude detection. Every promising signal has turned out to be a false alarm. Every candidate object has proven to be something else. The electronic hunters were about to learn that space is full of cosmic mimics and false prophets. The universe loves to play tricks on astronomers hunting for Planet 9. Every year brings dozens of promising candidates, faint, slowly moving objects detected at the very edge of telescope sensitivity. Each discovery triggers weeks of excitement, follow-up observations, and orbital calculations, only to end in the crushing disappointment of another false alarm. The hunt for Planet 9 has become a masterclass in cosmic deception. The most common imposters are distant asteroids masquerading as planets. These chunks of rock and ice orbit in the asteroid belt between Mars and Jupiter. But when they reach the far side of their orbits, they appear to move slowly against background stars, exactly like Planet 9 would appear. Only careful observations over several months can reveal their true nature. Think of it like mistaking a distant airplane for a slow-moving satellite. From far away, a fast object can appear to crawl across the sky, creating the illusion of something much more distant and exotic. Asteroids at opposition, when Earth lies directly between them and the Sun, create exactly this kind of optical illusion. Computer glitches add another layer of frustration to the search. Cosmic rays striking telescope detectors create bright spots that appear indistinguishable from stars or planets in individual images. Software algorithms designed to identify moving objects sometimes flag these random detector hits as potential Planet 9 candidates, sending astronomers on wild goose chases that lead nowhere. Hot pixels on camera sensors cause similar problems. These are individual detector elements that malfunction and record bright signals even when no light hits them. hot pixels appear in the same location in every image, but when the telescope moves between exposures, they can create the illusion of an object that appears to jump from place to place across the sky. One of the most heartbreaking false alarms occurred in 2018 when a team announced the discovery of an object they called far, far out, potentially the most distant object ever found in our solar system. Initial observations suggested it was 3 times farther from the Sun than Pluto, putting it squarely in Planet 9 territory. Months of follow-up observations revealed the devastating truth. Far, far out was indeed extremely distant, but it was just another Kuiper Belt object, larger than expected, but nowhere near massive enough to be Planet 9. The discovery was scientifically valuable but emotionally crushing for researchers who had hoped they'd found the holy grail of planetary science. Atmospheric distortions create their own brand of false hope. When starlight passes through Earth's atmosphere, it gets bent and distorted by pockets of air at different temperatures. This causes stars to appear to jump around slightly from image to image, creating artificial motion that can fool computer algorithms into flagging them as moving objects. The psychological toll of false alarms weighs heavily on Planet 9 hunters. Each promising candidate requires intense focus and hope, followed by the methodical process of determining its true nature. The repeated cycle of excitement and disappointment has become an occupational hazard for astronomers involved in the search. Some false alarms result from simple human error. Tired researchers working through the night sometimes misread coordinates, transpose numbers, or make calculation mistakes that turn ordinary asteroids into apparent Planet 9 candidates. The pressure to make the discovery of the century can cloud judgment and lead to wishful thinking. Statistical noise adds the final layer of confusion. When you're looking for something at the very limit of telescope sensitivity, random fluctuations in detector readings can create signals that look like faint moving objects. Only by taking multiple images over extended periods can astronomers separate real signals from statistical phantoms. Despite years of false alarms and dead ends, the search continues with undiminished intensity. Each failed candidate provides valuable information about where Planet 9 isn't, gradually narrowing the search zone. But the cosmic game of hide-and-seek was teaching astronomers that they needed to look beyond the obvious places. Sometimes the best way to find something invisible is to study the shadows it casts. While telescopes scan the skies for direct glimpses of Planet 9, a different breed of detective work is uncovering its fingerprints throughout the solar system. These cosmic forensics experts read gravitational scars like detectives examining a crime scene, finding evidence of Planet 9's influence in places no one thought to look. The first clue comes from the Kuiper Belt's sharp outer edge. Beyond about 50 times Earth's distance from the Sun, the population of small, icy objects drops off dramatically, as if something swept them away. Computer simulations show that Planet 9's gravity could have acted like a cosmic vacuum cleaner, either ejecting objects entirely from the solar system or shepherding them into the tilted orbits we observe today. Think of it like walking through a forest and finding a perfectly circular clearing where no trees grow. You don't need to see what created the clearing to know that something powerful was there. Planet 9's gravitational influence has carved similar clearings in the outer solar system, invisible to casual observation but obvious to those who know what to look for. The strange behavior of periodic comets provides another piece of the puzzle. These cosmic snowballs follow predictable paths that return them to the inner solar system every few decades or centuries. But some comets show subtle changes in their orbits that can't be explained by interactions with known planets. Comet Mach-Holtz follows a particularly suspicious path. Its orbit is tilted by about 60 degrees relative to the main plane of the solar system, and it approaches the Sun from a direction that aligns suspiciously well with Planet 9's predicted location. The odds of this being coincidental are vanishingly small. Even more intriguing is the population of objects called centaurs, small bodies that orbit between Jupiter and Neptune. These cosmic wanderers should be randomly distributed throughout the region, but instead they show a subtle bias towards certain orbital orientations. Computer models reveal that Planet 9's gravity could have nudged these objects into their current configuration over millions of years. The evidence extends all the way to the inner solar system. The orbits of the known planets show tiny discrepancies that have puzzled astronomers for decades. Mars arrives at certain points in its orbit a few seconds earlier than predicted. Jupiter's position differs from calculations by tiny but measurable amounts. These discrepancies are so small, they were attributed to measurement errors or incomplete knowledge of asteroid masses. But when astronomers add Planet 9 to their calculations, many of these tiny errors disappear. It's as if Planet 9 has been tugging on the other planets with invisible strings for billions of years. The timing of these gravitational effects provides crucial information about Planet 9's current location. Gravitational influences travel at the speed of light, so Planet 9's effect on the inner planets depends not just on its mass and distance, but on where it is right now in its enormously long orbit. By studying these timing discrepancies, astronomers can narrow down where Planet 9 should be in the sky at this moment. It's like triangulating the position of a radio transmitter by measuring the time it takes signals to reach different receivers. Recent studies of spacecraft trajectories have revealed additional anomalies. The Cassini probe, which spent 13 years orbiting Saturn, experienced tiny but persistent deviations from its predicted path. Similar effects have been detected in the trajectories of the Voyager probes as they journey toward interstellar space. These spacecraft anomalies are incredibly small, measured in millimeters per second, but they're consistent with gravitational perturbations from a massive object in the outer solar system. Each additional piece of evidence builds the case that Planet 9 isn't just hiding beyond Neptune, it's actively shaping the dynamics of our entire cosmic neighborhood. The indirect evidence has become so compelling that some astronomers argue we've already discovered Planet 9 through its gravitational effects, even though no one has seen it directly. But understanding how such a massive world could form so far from the Sun remains one of the greatest puzzles in planetary science. Building a world like Planet 9 in the outer solar system is like trying to construct a skyscraper with building materials scattered across an entire continent. The traditional theory of planetary formation works beautifully for the inner solar system, where Earth, Mars, Venus, and Mercury assembled from countless collisions of rocky debris. But it breaks down completely when applied to Planet 9's distant realm, where the raw materials for planet building are spread impossibly thin. Picture the early solar system as a giant construction site. Close to the Sun, the site is bustling with activity. Millions of rocky chunks colliding and sticking together like cosmic Lego blocks. But move outward beyond Neptune's orbit, and the construction site becomes a vast, nearly empty wasteland where building materials are separated by distances measured in millions of miles. The fundamental problem is density. In the region where Planet 9 orbits today, there simply wasn't enough solid material to build a world 10 times Earth's mass. The solar nebula, the disk of gas and dust from which planets formed, contained mostly hydrogen and helium at those distances, with only trace amounts of heavier elements needed to build rocky cores. Computer simulations reveal the cruel mathematics of distant planet formation. At Planet 9's predicted distance from the Sun, solid particles drift past each other at speeds measured in miles per hour. That sounds slow, but it's actually too fast for gravitational attraction to pull them together. Instead of sticking together to form larger objects, these cosmic building blocks simply bounce off each other and continue their lonely orbits. The situation gets worse when you consider the timescale problem. Planet formation is a race against time. The solar nebula, the source of hydrogen and helium gas needed to build giant planet atmospheres, only lasted about 10 million years before the young sun's energy blew it away. That's barely enough time for a massive planet to form close to the Sun, where conditions are ideal. At Planet 9's distance, the process would take 100 times longer. Think of it like trying to build a house during a 10-minute rainstorm, but your construction site is so remote that it takes an hour just to carry each piece of lumber to the foundation. By the time you've gathered enough materials to start building, the storm has passed, and you're left with an incomplete structure. The core accretion model, the standard explanation for how giant planets form, requires a solid core of at least 10 Earth masses before a planet can begin capturing significant amounts of gas from the surrounding nebula. But building such a massive core at Planet Nine's distance would take hundreds of millions of years, long after the gas has dissipated. Some astronomers have proposed alternative formation mechanisms that could work in the outer solar system. The gravitational instability model suggests that massive planets can form directly from the collapse of dense regions in the gas disk, without needing to build up solid cores first. This process works much faster, taking only thousands of years instead of millions, but it requires very specific conditions that may not have existed in our solar system. The streaming instability offers another possibility. This mechanism concentrates solid particles into dense clumps through complex interactions with the gas disk. Under the right conditions, these clumps can collapse directly into planetary cores, bypassing the slow collision-based process entirely. But even these alternative mechanisms struggle to explain how Planet 9 could have formed at its current location. The outer regions of the solar nebula were simply too sparse and too cold to support rapid planet formation through any known process. Recent studies of exoplanets have revealed that mini-Neptunes like Planet 9 are incredibly common around other stars, often orbiting much closer to their host stars than Planet 9 orbits the Sun. This observation has led to a revolutionary new theory about Planet 9's origin, one that doesn't require it to form where it currently resides. What if Planet 9 formed much closer to the Sun, where conditions were favorable for rapid planet growth, and then migrated outward to its present location through gravitational interactions with other planets? This migration scenario opens up entirely new possibilities for understanding how our solar system's most mysterious world came to be. Planet 9 might be in exile, banished from the inner solar system by gravitational warfare. The migration theory paints a dramatically different picture of our solar system's early history, one filled with planetary violence, gravitational battles, and cosmic refugees. Instead of forming peacefully at its current location, Planet 9 might have been born much closer to the Sun, only to be ejected to the outer darkness through a series of gravitational encounters that reshaped the entire solar system. Picture the early solar system as a cosmic pool table, with massive planets acting as cue balls striking each other in a chaotic game that lasted millions of years. In this violent environment, gravitational interactions could fling planets across enormous distances, turning orderly orbital arrangements into cosmic chaos. The story begins 4.5 billion years ago, when our solar system was still young and unsettled. Computer simulations suggest that the region between Jupiter and Neptune originally contained not 4 giant planets, but 5. The extra world, possibly Planet 9 itself, orbited somewhere between Saturn and Uranus in a configuration that was gravitationally unstable. Think of it like 5 people trying to sit on a 4-person bench. Someone has to give way, and in the early solar system, that someone was likely the smallest of the giant planets. Through a series of close gravitational encounters with Jupiter and Saturn, this 5th planet found itself in an increasingly eccentric orbit that eventually carried it far beyond Neptune's domain. The ejection process wasn't sudden or violent. Instead, it unfolded over millions of years through a mechanism astronomers call the 9’s model, named after the French city where it was developed, but pronounced Nice rather than nice. This model describes how gravitational interactions between the giant planets could have dramatically rearranged the outer solar system. Jupiter, the heavyweight champion of our solar system, played the role of cosmic bully in this scenario. Its immense gravity acted like a gravitational slingshot, accelerating smaller planets to higher speeds with each encounter. Over time, these repeated gravitational kicks could boost a planet's velocity enough to send it careening toward the outer solar system. But exile wasn't inevitable. Computer simulations show that roughly half of all ejected planets don't escape the solar system entirely. Instead, they end up in distant, highly elliptical orbits, exactly the kind of orbit predicted for Planet 9. These cosmic refugees retain enough gravitational connection to their birth star to remain bound, but they're banished to the cold outer reaches where they can no longer interfere with the remaining planets. The migration theory elegantly solves the formation problem that plagued astronomers. If Planet 9 formed closer to the Sun, perhaps at Jupiter's current distance, It would have had access to abundant building materials and could have grown to its predicted size within the 10 million year window before the solar nebula disappeared. The theory also explains several puzzling features of our solar system's architecture. The late heavy bombardment, a period about 4 billion years ago, when asteroids and comets rained down on the inner planets, could have been triggered by Planet 9's ejection. As the migrating planet passed through the asteroid belt and Kuiper belt, it would have scattered countless small objects into chaotic orbits that eventually collided with Earth, Mars, and other inner planets. The migration theory makes specific predictions about Planet 9's composition and internal structure. A world that formed closer to the Sun would have a different mixture of rock, ice, and gas than one that formed in the outer solar system. These differences could be detectable once Planet 9 is finally found and studied in detail. Recent discoveries of migrating planets around other stars support the plausibility of the migration scenario. The Kepler Space Telescope has found numerous examples of giant planets that clearly migrated from their birth locations to their current orbits. Migration appears to be a common, perhaps inevitable, part of planetary system evolution. But the migration theory faces one significant challenge: timing. Confirming the discovery of Planet 9 requires patience that spans human lifetimes. Even if a telescope captures the first photons of light from Planet 9 tomorrow, proving that the discovery is real would take years of painstaking observations that push current technology to its absolute limits. The observational challenges facing Planet 9 hunters make finding the world seem easy compared to confirming it actually exists. The fundamental problem is motion, or rather, the lack of it. Planet 9 moves so slowly across the sky that detecting its motion requires observations separated by months or even years. At its predicted distance from the Sun, Planet 9 would take between 10,000 and 20,000 years to complete a single orbit. That means it moves less than 2 arc-minutes per year, about 1/15 the width of the full moon. Think of it like trying to prove that the hour hand on a clock is moving by taking photographs a few minutes apart. The motion is real, but it's too slow to detect without extremely precise measurements over extended periods. Planet 9's motion against the background stars would be barely perceptible even to the most sensitive telescopes. The brightness challenge adds another layer of complexity. Planet 9 would appear as a faint, star-like point of light, indistinguishable from billions of actual stars in distant galaxies. Only by observing the same patch of sky repeatedly and looking for objects that move between exposures can astronomers separate planets from the cosmic background. But even detecting motion isn't enough to confirm a Planet 9 discovery. Asteroids, comets, and other solar system objects also move against background stars, often at rates similar to what Planet 9 would show. Distinguishing between a distant planet and a closer asteroid requires precise measurements of the object's brightness, color, and orbital characteristics. The orbital calculation process is particularly demanding. Confirming that an object follows the predicted Planet 9 orbit requires tracking its position for at least one complete orbit, which could take 20,000 years. Obviously, astronomers can't wait that long for confirmation. Instead, they must observe the object for several years and use the small arc of its orbit to extrapolate the complete orbital path. This extrapolation process is like trying to determine the shape of a giant circle by examining only a tiny curved segment. Small measurement errors can lead to dramatically different orbital predictions, making it easy to mistake a small asteroid for a distant planet or vice versa. Weather and atmospheric conditions add unpredictable variables to the confirmation process. Planet 9 observations require the darkest possible skies, with no moon visible and minimal atmospheric turbulence. Such conditions occur only a few nights per month at the world's best observatory sites, and even then, clouds or high winds can shut down observations entirely. The faintness of Planet 9 means that each observation requires hours of exposure time to collect enough photons for precise measurements. During these long exposures, the Earth's rotation causes stars to drift across the telescope's field of view, requiring sophisticated tracking systems to keep the telescope pointed precisely at the target. Cosmic ray strikes on telescope detectors create additional complications. These high-energy particles from deep space randomly hit the electronic sensors, creating bright spots that can mimic the appearance of faint astronomical objects. Distinguishing real planets from cosmic ray hits requires taking multiple images and comparing them carefully. The psychological challenges facing Planet 9 hunters may be as demanding as the technical ones. Years of false alarms and disappointing results have created a scientific environment where extraordinary claims require extraordinary evidence. Any announced Planet 9 discovery will face intense scrutiny from skeptical colleagues who demand multiple independent confirmations. The competition between different research teams adds pressure to announce discoveries quickly, but premature announcements can damage scientific reputations if the claims don't hold up under scrutiny. The balance between being first to announce a discovery and being certain the discovery is real creates enormous stress for astronomers involved in the search. Despite these challenges, the search continues with unprecedented intensity, driven by the knowledge that finding Planet 9 would represent one of the greatest discoveries in the history of astronomy. But they weren't searching alone. Teams around the world were joining the hunt with increasingly sophisticated strategies. The hunt for Planet 9 has become the most competitive treasure hunt in modern astronomy. Around the globe, rival teams of astronomers are racing against each other and against time, each hoping to claim the discovery that will secure their place in history alongside Galileo and Kepler. This isn't just scientific collaboration anymore. It's a high-stakes competition where the winner takes everything and the losers are forgotten footnotes in astronomy textbooks. The Subaru telescope team in Hawaii leads one of the most systematic searches, using their wide-field camera to methodically scan the northern sky in a grid pattern that ensures no potential hiding spot goes unexplored. Led by astronomer Scott Shepard, this team has already discovered dozens of new objects in the outer solar system, each one providing additional clues about Planet 9's gravitational influence. Their strategy focuses on the opposition region, the part of sky directly opposite the Sun, where Planet 9 would appear brightest and show the most motion against background stars. Night after night, they return to the same patches of sky, looking for anything that moves between exposures. It's methodical, patient work that requires the discipline of monks and the precision of surgeons. Meanwhile, the Dark Energy Survey team takes a different approach, mining their enormous database of southern sky images for objects that previous searches missed. Their survey wasn't designed to find planets, but it covers such a vast area and reaches such faint magnitudes that it might accidentally capture Planet 9 in its digital net. Think of it like two different fishing strategies. The Subaru team uses precision fishing with carefully chosen bait in specific locations. The Dark Energy Survey team casts enormous nets across vast stretches of ocean, hoping to catch something valuable among the millions of objects in their haul. The competition extends beyond individual teams to entire countries. Japan's leadership in wide-field astronomy through the Subaru telescope represents a national investment in astronomical discovery. American teams, supported by NASA and the National Science Foundation, bring different technological advantages to the hunt. European astronomers contribute their own sophisticated search strategies through facilities like the Very Large Telescope in Chile. Each team guards their search strategies and preliminary results with the secrecy typically reserved for military operations. Astronomical conferences have become diplomatic battlegrounds where teams share just enough information to maintain scientific credibility while holding back the crucial details that might give competitors an advantage. The stakes couldn't be higher. The team that finds Planet 9 will secure Nobel Prize consideration, permanent fame in astronomy, and funding for future research projects that will last their entire careers. The discovery will be named after the lead investigator, ensuring immortality in the same way that Uranus honors William Herschel and Neptune honors John Couch Adams. But the competition has also driven innovation in search techniques and data analysis methods. Teams push their instruments to detection limits that were unimaginable just a decade ago. They develop new algorithms for identifying moving objects, new strategies for eliminating false positives, and new ways to squeeze maximum information from every photon of light their telescopes collect. The rivalry has created redundancy that benefits science as a whole. Multiple independent searches increase the chances that Planet 9 will be found, and they provide cross-checks that reduce the likelihood of false discoveries, making it into the scientific literature. As the search intensifies and technology improves, the discovery of Planet 9 feels increasingly inevitable. The question is no longer if it will be found, but when and by whom. Inside powerful supercomputers, digital versions of our solar system are revealing Planet 9's secrets. While telescopes scan the real sky for glimpses of our mysterious ninth planet, computer scientists are building virtual solar systems where they can fast forward through billions of years of planetary evolution in a matter of hours. These digital universes have become the secret weapon in the hunt for Planet 9, predicting where it should be hiding and how it got there. The most sophisticated simulations start with the solar system as it existed 4.5 billion years ago, a chaotic disk of gas, dust, and countless planetary embryos orbiting a young, violent sun. The computers then calculate how gravity pulls on every object, tracking millions of interactions as the system slowly evolves into its current configuration. Think of it like playing the ultimate video game, where every particle follows the laws of physics with perfect precision. The game runs at super speed, with each second of computer time representing millions of years of real history. Scientists can pause the simulation, rewind it, or change the starting conditions to see how different scenarios play out. These virtual experiments have revealed stunning insights about Planet 9's role in shaping our solar system. In simulations that include a massive ninth planet, the outer solar system evolves into something that looks remarkably like what we observe today. Remove Planet 9 from the simulation, and the virtual solar system becomes chaotic, with objects scattered randomly instead of clustering in the precise patterns we see in reality. The simulations work by solving what mathematicians call the n-body problem, calculating how multiple objects influence each other through gravity. For Planet 9 simulations, that means tracking the gravitational interactions between the Sun, 8 known planets, thousands of asteroids and comets, and the hypothetical ninth planet itself. Modern supercomputers can handle these calculations, but barely. A single simulation tracking the evolution of our solar system over 4 billion years requires weeks of computation time on machines that cost millions of dollars. The calculations are so intensive that research teams must compete for time on national supercomputer facilities, submitting proposals that are evaluated like requests for telescope time. The simulations have predicted several key features of Planet 9 that guide observational searches. They suggest the planet should have a mass between 5 and 20 times Earth's mass, orbit between 400 and 800 times farther from the Sun than Earth, and follow a highly elliptical path that takes 15,000 to 25,000 years to complete. But the simulations also reveal a frustrating truth. Planet 9 could be almost anywhere, within an enormous search zone. Its orbit is so elongated that it spends most of its time at vast distances where it appears incredibly faint. The simulations show that Planet 9 is most likely to be near aphelion, the farthest point in its orbit, where it would be almost impossible to detect with current telescopes. Recent simulations have explored increasingly exotic scenarios. What if Planet 9 isn't alone, but part of a binary system with another massive object? What if it has a large moon that affects its motion? What if it's actually two smaller planets orbiting close together? Each possibility changes the predictions and opens new search strategies. The most intriguing simulations explore Planet 9's past. Computer models suggest that if Planet 9 formed closer to the Sun and migrated outward, it should have left a trail of evidence in the form of displaced asteroids and comets. These gravitational scars should still be visible today, providing a roadmap to Planet 9's migration history. The simulations have also predicted the discovery of additional objects that should cluster with Planet 9's gravitational influence. Several of these predicted objects have actually been found by observational surveys, providing powerful confirmation that the computer models are on the right track. As computing power increases and algorithms improve, the simulations are becoming precise enough to predict not just where Planet 9 should be, but when it will be easiest to find during its enormously long orbit. But even the most sophisticated computer model can't overcome the fundamental challenge of detecting something so distant and dark. Planet 9 dances to gravitational music that takes 20,000 years to complete a single song. Understanding Planet 9's orbit requires thinking in timescales that dwarf human civilization. While Earth completes its familiar yearly journey around the Sun, Planet 9 crawls through space so slowly that it has barely moved since the pyramids were built. Its orbital mechanics operate on a scale that transforms our understanding of what it means to be a planet in our solar system. The mathematics of Planet 9's orbit read like poetry written in the language of physics. Its path around the Sun stretches into an enormous ellipse, not the nearly circular orbit that Earth follows, but a cosmic egg shape that carries it from relatively close to the Sun all the way out to the edge of interstellar space. At perihelion, its closest approach to the Sun, Planet 9 still orbits farther out than Neptune, maintaining its status as the most distant major planet. But at aphelion, its farthest point, it ventures out to nearly 1,000 times Earth's distance from the Sun. At that remote location, the Sun appears as just another bright star, providing less warmth than a candle flame viewed from across a football field. Think of Planet 9's orbit like a cosmic roller coaster that takes 20 millennia to complete a single ride. For most of that journey, Planet 9 cruises through the outer reaches, where it moves at walking speed relative to the background stars. Only during its brief passage through the inner part of its orbit does it accelerate to the relatively breakneck pace of a few miles per second. The orbital mechanics explain why Planet 9 has remained hidden for so long. It spends roughly 90% of its orbital period in the outer reaches of its elliptical path, where it appears incredibly faint and moves almost imperceptibly against the star background. Current telescope surveys are most likely to spot it during the brief periods when it ventures into the relatively inner parts of its orbit. But here's the cruel irony. Planet 9's orbital mechanics suggest it might currently be near aphelion, at its farthest and faintest point. If true, it could remain essentially undetectable for centuries, slowly brightening as it begins the 10,000-year journey back toward perihelion. The gravitational choreography becomes even more complex when you consider Planet 9's interactions with the other planets. Its immense orbit carries it through gravitational territories, controlled by different planets at different times. Sometimes it feels the distant tug of Jupiter's gravity. Other times it responds to Neptune's influence. These competing gravitational forces create subtle perturbations in its orbit that could provide clues to its current location. The orbital inclination adds another layer of complexity. Planet 9's orbit is tilted about 15 to 25 degrees relative to the plane where the other planets orbit. This means it spends part of its time above the plane of the solar system and part of its time below, like a cosmic Ferris wheel tilted at an angle. This tilted orbit has profound implications for the search strategy. Planet 9 could currently be located far above or below the plane where most astronomical surveys focus their attention. Telescopes optimized for finding objects in the plane of the solar system might be looking in entirely the wrong direction. The orbital mechanics also influence Planet 9's rotation and internal structure. Planet 9 might be playing the ultimate game of cosmic hide-and-seek by hiding in the wrong century. The cruel mathematics of orbital timing could explain why the most intensive planet hunt in history has come up empty-handed. Planet 9's enormously long orbit means that its brightness and visibility change dramatically over timescales measured in thousands of years. We might simply be living in the wrong era to spot our solar system's most elusive member. Consider the timeline problem from Planet 9's perspective. If it completes one orbit every 20,000 years, then human civilization has existed for less than half of one orbital period. The entire history of astronomy and NTs, from Galileo's first telescope to today's digital sky surveys, represents just 2% of Planet 9's year. During most of its orbital journey, Planet 9 lurks in the outer darkness where it reflects barely enough sunlight to register on even the most sensitive telescopes. But for perhaps 1,000 or 2,000 years out of every 20,000, it ventures close enough to become detectable with technology like ours. Think of it like a lighthouse with an incredibly long rotation period. For most of the time, its beam points away from you into empty space. Only occasionally does the beam sweep across your location, briefly illuminating everything before disappearing again for decades or centuries. The observational window for Planet 9 detection might be as narrow as a few centuries out of every 20 millennia. If Planet 9 reached its closest approach to the Sun during the time of ancient Rome, it would have appeared as a faint, star-like object visible to telescopes that wouldn't be invented for another 1500 years. By the time astronomers developed the tools to find it, Planet 9 would have already begun its journey back to the outer darkness. Alternatively, Planet 9 might currently be approaching its closest point to the Sun, gradually brightening over the coming centuries until it becomes easily detectable. In this scenario, future astronomers might wonder how 21st century scientists could have missed something so obvious. The timing problem extends beyond simple brightness considerations. Planet 9's motion against background stars also varies dramatically depending on where it is in its orbit. Near perihelion, it would appear to move relatively quickly, making it easier to distinguish from background stars and galaxies. Near aphelion, its motion becomes so slow that it could take years to confirm that it's actually moving at all. Current estimates suggest Planet 9 might be anywhere from 400 to 800 times farther from the Sun than Earth. That enormous uncertainty translates into vastly different predictions for its brightness and detectability. At 400 times Earth's distance, Planet 9 might be just barely detectable with current telescopes. At 800 times Earth's distance, it could remain invisible for decades to come. The timing problem creates a paradox for Planet 9 hunters. The longer the search continues without success, the more likely it becomes that Planet 9 is simply too faint to detect with current technology. But giving up the search means potentially missing the discovery of the century if Planet 9 happens to be brightening as it approaches perihelion. Recent studies have attempted to constrain Planet 9's orbital phase by analyzing the clustering of distant objects it influences. Some models suggest Planet 9 is currently near aphelion, explaining why it has eluded detection despite intensive searches. But even if Planet 9 is currently too faint to see, astronomers are developing new strategies that don't require direct detection. Finding Planet 9 requires pushing the limits of what darkness means in the cosmos. The brutal mathematics of brightness and distance conspire to make Planet 9 one of the faintest objects astronomers have ever attempted to detect. Understanding just how dim this world appears requires thinking about light in ways that challenge human intuition and push telescope technology to its absolute breaking point. Brightness in astronomy follows an unforgiving law called the inverse square rule. Double the distance to an object, and it appears 4 times fainter. Triple the distance, and it becomes 9 times dimmer. Planet 9 orbits so far from the Sun that this mathematical cruelty transforms a world the size of Neptune into something barely brighter than a flickering candle viewed from 3,000 miles away. The calculations start with sunlight itself. At Earth's distance, the Sun delivers about 1,300 watts of energy per square meter, enough to power a hairdryer. But at Planet 9's predicted location, that same sunlight has spread out over such an enormous area that each square meter receives less than 1 watt of energy. It's like trying to heat a house with a birthday candle. Planet 9 doesn't generate its own light. It merely reflects the feeble sunlight that reaches it after traveling hundreds of billions of miles from the Sun. The amount of light it reflects depends on its albedo, the fraction of incoming sunlight that bounces back toward Earth instead of being absorbed by its surface or atmosphere. Think of albedo like the difference between a mirror and a piece of charcoal. Fresh snow reflects about 90% of the light that hits it, while charcoal reflects less than 5%. Most objects in the outer solar system are dark, closer to charcoal than snow, which makes them even harder to see than their enormous distances would suggest. If Planet 9 has an albedo similar to Neptune, has reflecting about 40% of incoming light, it would appear as a 25th magnitude object in the most powerful telescopes. That's about 10 million times fainter than the faintest stars visible to the naked eye. If its surface is darker, Like most objects in the Kuiper belt, it could be 26th or even 27th magnitude, so faint that detecting it would push current telescope technology beyond its design limits. The brightness calculations become even more pessimistic when you consider atmospheric absorption. Earth's atmosphere absorbs and scatters light, making faint objects appear even dimmer. On the best nights at the highest mountaintop observatories, atmospheric effects still steal about 20% of the light from distant objects. But astronomers have found ways to fight back against the darkness. Modern telescope detectors are so sensitive they can register individual photons of light. Image processing techniques can enhance faint signals by combining multiple exposures and filtering out noise. Adaptive optics systems use flexible mirrors to counteract atmospheric turbulence, producing images nearly as sharp as those from space telescopes. The search for Planet 9 has driven the development of new brightness measurement techniques that squeeze every possible photon from the darkness. Some teams use infrared detectors that might catch the faint heat signature Planet 9 radiates into space. Others are preparing for the next generation of ground-based telescopes that will have mirrors 4 times larger than anything currently available. New discoveries are either confirming Planet 9's existence or challenging everything we thought we knew. Every few months, astronomers announce the discovery of another distant object in the outer solar system, and each new find becomes a cosmic litmus test for Planet 9's reality. These discoveries either strengthen the case for a hidden ninth planet or force scientists to reconsider whether the clustering they've observed is as meaningful as they believed. The object called the Goblin, officially designated 2015 TG 387, provided one of the strongest confirmations of Planet 9's influence. Discovered in 2015, but not announced until 3 years later, the Goblin follows an orbital path that aligns perfectly with Planet 9 predictions. Its closest approach to the Sun brings it to about 65 times Earth's distance, still farther than any known planet, while its farthest point carries it out to nearly 2,300 times Earth's distance. Think of the Goblin as a cosmic messenger, carrying news from the outer darkness about the gravitational forces that shape its path. Computer simulations show that without Planet 9's influence, the Goblin's orbit should be chaotic and unstable. But with a massive ninth planet shepherding its motion, the Goblin's path becomes stable and predictable over millions of years. The discovery of Far Out 2018 VG18 added another piece to the puzzle. This object currently holds the record as the most distant known member of our solar system, orbiting at about 120 times Earth's distance from the Sun. While Far Out doesn't show the extreme orbital clustering of other Planet 9 candidates, its existence proves that substantial objects can survive in the outer reaches where Planet 9 supposedly lurks. But not every new discovery supports the Planet 9 hypothesis. The object called 2018 VP1, nicknamed Dragonfly, follows an orbit that doesn't fit the clustering pattern at all. Its orbital orientation points in the wrong direction, and its path doesn't show the extreme elongation expected from Planet 9's gravitational influence. These non-conforming objects pose a serious challenge to the Planet 9 theory. If a massive planet is really shepherding objects in the outer solar system, why don't all distant objects show the same orbital characteristics? The discovery of even one object that clearly contradicts Planet 9's predicted influence could undermine the entire hypothesis. Some astronomers argue that the non-conforming objects actually strengthen the case for Planet 9 by providing a control group. According to this interpretation, Planet 9 only influences objects that venture into specific regions of space during their orbits. Objects like Dragonfly that avoid these regions should show random orbital orientations, exactly as observed. The statistical significance of the clustering continues to grow stronger with each new discovery that fits the pattern. What started as a curious coincidence involving 6 objects has evolved into a robust pattern involving more than a dozen distant worlds. The odds of such clustering occurring randomly have dropped to less than 1 in several thousand. But the statistics also reveal troubling gaps in the data. Most of the clustering objects were discovered by the same research teams using similar survey techniques. This observation bias might create artificial clustering that has nothing to do with Planet Nine's gravitational influence. Recent studies have attempted to address these concerns by analyzing objects discovered by independent surveys using different search strategies. The clustering signal remains strong even when observation bias is taken into account, but the statistical significance is somewhat reduced. The debate over alternative clustering has forced astronomers to develop more sophisticated methods for analyzing orbital data and accounting for observational biases. As more objects are discovered and analyzed, the cosmic jury is still deliberating on Planet Nine's guilt or innocence. Planet Nine's fate might have been decided by stellar neighbors that disappeared billions of years ago. The story of Planet Nine cannot be told without understanding the crowded stellar nursery where our solar system was born. 4.5 billion years ago, the Sun wasn't the isolated star we know today, but a member of a bustling stellar community where hundreds of young stars formed, lived, and interacted in ways that permanently shaped the architecture of planetary systems. In those chaotic early days, passing stars regularly ventured close enough to our solar system to disrupt planetary orbits through their gravitational influence. These stellar encounters, some closer than the current distance to Pluto, could have been responsible for flinging Planet Nine into its current distant orbit or even capturing it from another star system entirely. Think of the early stellar cluster like a cosmic dance floor where partners constantly changed. Stars would approach each other, perform a gravitational waltz that lasted thousands of years, then separate and move on to new partners. During these encounters, planets could be stolen, ejected, or dramatically relocated within their host systems. Computer simulations of these ancient stellar encounters reveal that close approaches between stars were not rare cosmic accidents, but inevitable consequences of stellar formation in dense clusters. The young Sun likely experienced dozens of close encounters with neighboring stars during its first 100 million years of existence. The closest encounters could have approached within 50 times Earth's distance from the Sun, close enough to completely reshape the outer solar system. During such encounters, the gravitational tug-of-war between two stars could easily fling massive planets into highly elliptical orbits, or even eject them from the solar system entirely. Recent studies suggest that stellar encounters might explain not just Planet Nine's existence, but also several other puzzles about our solar system's architecture. The unusual orbits of objects in the Kuiper Belt, the tilted spin axis of Uranus, and even the orbital characteristics of some Jupiter's moons might all bear the gravitational scars of ancient stellar encounters. The stellar influence theory makes specific predictions about Planet Nine's properties that could be tested once it's discovered. A planet that was displaced by stellar encounters should show chemical and isotopic signatures that reflect its formation location, not its current position. If Planet 9 formed closer to the Sun, but was kicked outward by stellar encounters, its composition should resemble that of Uranus and Neptune rather than the ice-rich objects in the Kuiper Belt. The timing of stellar encounters also matters. Most of the Sun's birth cluster dispersed within the first 100 million years, taking the disruptive stellar neighbors with them. This means any major orbital disruptions, including Planet Nine's ejection to its current orbit, must have occurred very early in solar system history. The dispersal of the birth cluster might have saved Planet Nine from complete ejection. Computer simulations show that if stellar encounters had continued for longer periods, Planet Nine would likely have been expelled from the solar system entirely, becoming a rogue planet drifting alone through interstellar space. The stellar influence extends beyond individual planet trajectories to affect the entire structure of the outer solar system. The same encounters that shaped Planet Nine's orbit could have scattered countless smaller objects, creating the extended disk of debris that we observe today in the Kuiper Belt and Oort cloud. Understanding stellar influences on planetary system evolution has become a crucial component of exoplanet research, as astronomers study how planetary systems around other stars might have been shaped by similar processes. The ghost of ancient stellar encounters continues to haunt our solar system, leaving gravitational fingerprints that point toward a hidden world shaped by forces from the cosmic deep. The hunt for Planet 9 has evolved into a technological arms race between human ingenuity and cosmic darkness. Astronomers have abandoned the traditional approach of simply pointing telescopes at the sky and hoping to spot Planet 9 through luck or persistence. Instead, they've developed sophisticated strategies that combine multiple wavelengths of light, advanced computer algorithms, and even theoretical physics to track down our solar system's most elusive resident. The infrared approach represents one of the most promising new directions. While Planet 9 reflects very little visible sunlight, it might still be warm enough from its formation 4.5 billion years ago to emit detectable infrared radiation. Objects the size of Neptune retain internal heat for billions of years, glowing like cosmic embers in the darkness of space. NASA's Wide Field Infrared Survey Explorer spacecraft has already scanned most of the sky in infrared light, and scientists are mining that data for slow-moving objects that previous analyses missed. The challenge lies in distinguishing Planet 9's faint infrared glow from the billions of background stars and galaxies that also emit heat radiation. Think of it like trying to spot a single warm coal in a field full of campfires. The coal might be glowing, but it's vastly outnumbered by brighter heat sources that can mask its presence. Advanced image processing techniques can filter out known background objects, but Planet 9's signal might still be buried in statistical noise. The parallax method offers another detection strategy that doesn't require Planet 9 to be particularly bright. As Earth orbits the Sun, our perspective on distant objects shifts slightly, a phenomenon called parallax. Objects within our solar system show measurable parallax shifts, while background stars are too distant to show any noticeable motion. By comparing images taken 6 months apart, when Earth is on opposite sides of its orbit, astronomers can identify objects that show parallax motion characteristic of solar system membership. This technique works even for objects too faint to be visible in single exposures, as long as they can be detected when multiple images are combined. The occultation strategy relies on Planet 9 passing in front of background stars, temporarily blocking their light. While the chances of observing such an occultation are extremely small, networks of small telescopes monitoring thousands of stars simultaneously might catch Planet 9 in the act of eclipsing a distant sun. Machine learning algorithms have revolutionized the search by automating the analysis of millions of astronomical images. These artificial intelligence systems can identify patterns and anomalies that human astronomers might miss, processing data far faster than any human-led analysis could achieve. The algorithms learn to recognize the subtle signatures of planetary motion by training on known examples of asteroids and comets. Once trained, they can scan through archive images, looking for similar patterns that might indicate the presence of undiscovered objects. Gravitational microlensing represents perhaps the most exotic detection strategy. If Planet 9 passes directly between Earth and a distant background star, its gravity would bend the star's light, like a cosmic magnifying glass, causing the star to appear temporarily brighter. The duration and characteristics of this brightening would reveal Planet 9's mass and distance. Some teams are even exploring the possibility of detecting Planet 9 through its effects on spacecraft trajectories. Ultra-precise tracking of distant space probes might reveal tiny deviations caused by Planet 9's gravitational pull, providing an indirect way to constrain its location and mass. The most ambitious detection strategies involve coordinating multiple telescopes around the world to simultaneously monitor different parts of the predicted search zone, maximizing the chances of catching Planet 9 during the brief periods when it might be detectable. But success might ultimately depend on tools that don't yet exist. The case for Planet 9 rests on mathematical evidence so compelling it approaches the realm of certainty. In science, statistical significance is the difference between interesting coincidence and revolutionary discovery. For Planet 9, the statistical analysis has evolved from curious observation to mathematical proof that something massive is lurking in the outer solar system, even if we can't see it directly. The numbers tell a story that becomes more convincing with each new discovery. When only 6 objects showed the mysterious orbital clustering, skeptics could argue for cosmic coincidence. But as more distant objects have been found following similar patterns, the probability of random chance has plummeted to levels that strain scientific credibility. Think of statistical significance like a cosmic court case where evidence accumulates until reasonable doubt disappears. Each new clustered object is another witness testifying to Planet Nine's existence. Each computer simulation that requires a massive ninth planet to explain the observations is another piece of forensic evidence pointing toward the same inescapable conclusion. The current statistical significance of the Planet 9 hypothesis exceeds 4 sigma scientific language, meaning the odds of the observed clustering occurring by random chance are less than 1 in 15,000. In most fields of science, 3 sigma is considered strong evidence, and 5 sigma constitutes proof. Planet 9 is approaching the threshold where denial becomes mathematically untenable. But statistical analysis in astronomy faces unique challenges that don't exist in laboratory sciences. Astronomical observations are contaminated by selection biases, incomplete data, and the fundamental problem that we can only observe the universe from one location at one moment in cosmic time. The most significant bias comes from the discovery process itself. Most of the objects supporting Planet 9 were found by the same research teams using similar survey techniques. This creates the possibility that the clustering is an artifact of how and where astronomers choose to search, rather than evidence of genuine physical clustering. Recent studies have attempted to address this concern through what statisticians call bootstrap analysis. This technique involves randomly removing objects from the dataset and checking whether the clustering signal remains strong. The Planet 9 signal survives these tests, suggesting it's not simply a statistical fluke created by small sample sizes. The false discovery rate represents another statistical concern. With thousands of astronomers searching for patterns in astronomical data, some significant-looking correlations will occur purely by chance. The question isn't whether any individual pattern is statistically significant, but whether it remains significant after accounting for all the other patterns that were tested and rejected. Bayesian analysis provides a more sophisticated approach to the Planet 9 problem by incorporating prior knowledge about planetary formation and solar system dynamics. This statistical framework asks not just whether the clustering is unlikely to occur by chance, but whether Planet 9 provides the most plausible explanation compared to alternative hypotheses. The Bayesian approach strongly favors Planet 9 over alternatives like primordial black holes or modifications to gravity. While these exotic explanations can technically account for the observations, they require invoking phenomena that are much rarer and less well understood than conventional planets. Monte Carlo simulations represent the cutting edge of Planet 9 statistical analysis. These computer experiments create thousands of virtual solar systems with different starting conditions and evolutionary histories, then determine what fraction of them naturally evolved to show the clustering patterns we observe. The results are striking. Less than 1% of simulated solar systems without Planet 9 develop the kind of orbital clustering seen in real observations. But when Planet 9 is included in the simulations, clustering becomes the expected outcome rather than a rare coincidence. The statistical case has become so strong that the burden of proof has shifted to Planet 9 skeptics, who must now explain how such compelling mathematical evidence could arise without a massive ninth planet pulling the gravitational strings. Planet 9 might be the key to understanding thousands of alien worlds orbiting distant stars. The search for our solar system's hidden ninth planet has revealed profound connections to the study of exoplanets, worlds orbiting other stars throughout the galaxy. These connections suggest that finding Planet 9 wouldn't just complete our understanding of our own cosmic neighborhood, but could revolutionize how we interpret the architecture of planetary systems across the universe. The most striking connection involves the abundance of super-Earths and mini-Neptunes around other stars. Space telescopes like Kepler and TESS have discovered that planets with masses between Earth and Neptune are incredibly common in the galaxy. They're actually the most abundant type of planet we've found. Yet our solar system appeared to lack any planets in this crucial size range. Planet 9 fills that gap perfectly. If it exists as predicted, our solar system joins the cosmic mainstream by hosting a super-Earth or mini-Neptune in the same mass range that dominates planetary systems around other stars. This would transform our solar system from a cosmic oddball into a representative example of how planetary systems typically evolve. Think of it like discovering that your supposedly unique family actually follows patterns common to families everywhere. Planet 9 would make our solar system normal rather than exceptional, providing crucial insights into the standard processes of planetary formation and evolution. The orbital characteristics predicted for Planet 9 also match patterns observed in exoplanet systems. Many stars host super-Earths and mini-Neptunes in highly elliptical orbits that carry them far from their host stars. These distant, eccentric orbits were puzzling until astronomers realized they could result from gravitational interactions with other planets or nearby stars. Planet 9's predicted orbit, highly elliptical and tilted relative to the other planets, it's perfectly with theoretical models of how planetary systems evolve through gravitational interactions. Its existence would provide a local example of processes that shape planetary systems throughout the galaxy. The formation scenarios proposed for Planet 9 also have direct applications to exoplanet studies. If Planet 9 formed closer to the Sun and migrated outward through gravitational interactions, it would represent a textbook example of planetary migration, one of the most important processes in exoplanet evolution. Planetary migration explains many puzzling features of exoplanet systems, including giant planets that orbit extremely close to their stars and planetary systems with architectures completely unlike our own. Planet 9 would provide the first detailed case study of migration in our own solar system, allowing astronomers to test and refine their migration models. The detection techniques developed for Planet 9 hunting are already being applied to the search for exoplanets. Methods for identifying faint, slowly moving objects in astronomical images have improved the ability to detect distant exoplanets through direct imaging. Statistical techniques for analyzing clustering patterns are being used to identify multiple planet systems around other stars. Perhaps most importantly, Planet 9 could provide insights into planetary system stability. Computer simulations suggest that planetary systems with architectures similar to ours, including a distant super-Earth like Planet 9, might be more stable over billions of years than systems without such outer burette. Guardians. If true, this would have profound implications for the search for habitable exoplanets. Stable planetary systems are more likely to maintain the consistent conditions needed for life to evolve and flourish. Planet 9 might be a crucial component in making our solar system suitable for complex life. The study of Planet 9 has already advanced our understanding of how gravitational interactions shape planetary systems, how planets migrate during their formation, and how planetary architectures evolve over billions of years. These insights will prove invaluable as we study the thousands of exoplanets waiting to be discovered in the coming decades. The next decade will either discover Planet 9 or prove that it doesn't exist. There's no middle ground left. The technological revolution in astronomy is about to reach a tipping point that will definitively resolve the Planet 9 mystery one way or another. New telescopes, advanced detectors, and revolutionary search strategies are converging to create detection capabilities that dwarf anything available to previous generations of planet hunters. The Vera C. Rubin Observatory in Chile represents the most ambitious ground-based survey ever attempted. Starting operations in the mid-2020s, this facility will photograph the entire visible sky every few nights with unprecedented depth and precision. Its giant digital camera will capture images containing over 3 billion pixels, creating a time-lapse movie of the cosmos that reveals anything moving against the background stars. Think of the Rubin Observatory as a cosmic security camera with perfect memory and infinite patience. It will automatically detect and track every moving object brighter than 25th magnitude across the entire southern sky. If Planet 9 is anywhere within its detection limits, the Rubin Observatory will find it within its first few years of operation. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, will extend the search into infrared wavelengths, where Planet 9 might be most easily detected. Its position above Earth's atmosphere will provide crystal-clear images, free from the distortions that limit ground-based telescopes. The Roman telescope's infrared sensitivity could detect Planet 9's faint heat glow at distances where reflected sunlight becomes undetectable. But the most exciting developments might come from unexpected directions. Artificial intelligence algorithms trained on the distinctive signatures of planetary motion are becoming sophisticated enough to identify Planet 9 even in archival images where human analysts missed it. These digital archaeologists are excavating decades of astronomical data, looking for faint signals that earlier searches overlooked. The breakthrough might come from gravitational wave detectors, instruments originally designed to detect ripples in space-time from colliding black holes. If Planet 9 has a large moon or binary companion, the orbital motion might create detectable gravitational wave signals that could pinpoint its location without requiring any light at all. Interplanetary spacecraft are becoming sensitive enough to detect Planet 9's gravitational influence directly. The Parker Solar Probe, New Horizons, and Voyager spacecraft all carry instruments capable of measuring tiny deviations in their trajectories. A coordinated analysis of multiple spacecraft paths might triangulate Planet 9's position through gravitational forensics. The James Webb Space Telescope, already revolutionizing our understanding of the early universe, might stumble across Planet 9 while conducting deep infrared surveys. Its incredible sensitivity and resolution could detect Planet 9 as a moving infrared source, distinguishing it from background objects through precise photometry and spectroscopy. Even more futuristic detection methods are being developed. Proposals for gravitational microlensing surveys could detect Planet 9 through its gravitational effects on background starlight. Networks of small robotic telescopes might catch Planet 9 transiting in front of distant stars, revealing its size and orbital characteristics. The convergence of these technologies creates a detection net so comprehensive that Planet 9 would need to be extraordinarily well hidden to avoid discovery much longer. If it exists within the mass and distance ranges predicted by current models, multiple independent detection methods should find it within the next decade. But if Planet 9 remains undetected despite these technological advances, that absence will become just as scientifically significant as a positive detection. The null result would force astronomers to reconsider fundamental assumptions about planetary formation, gravitational dynamics, and the architecture of our solar system. The stage is set for the final act in one of astronomy's greatest detective stories. The search for Planet 9 has revealed that our solar system still holds secrets waiting to be discovered in the cosmic dark. From the first mysterious orbital alignments that hinted at an invisible puppet master, to the sophisticated computer simulations that map its gravitational influence, we've followed the mathematical breadcrumbs, leading to what might be the most significant planetary discovery since Neptune. The evidence has transformed from curious coincidence to compelling proof that something massive is shaping the outer solar system from the shadows. Whether Planet 9 is a super-Earth exile banished by gravitational warfare, a rogue world captured from another star, or something even more exotic, its discovery would fundamentally change our understanding of planetary formation and solar system evolution. We would learn that our cosmic neighborhood is far more dynamic and violent than we imagined, shaped by forces that operate on timescales that dwarf human history. But Planet 9 represents something deeper than just another world to add to our solar system census. It embodies the power of human curiosity to detect the invisible, to read gravitational signatures like cosmic fingerprints, and to use mathematics as a tool for exploring the universe's hidden architecture. The search has pushed telescope technology to its limits, developed new techniques for finding faint objects, and created computer simulations sophisticated enough to fast-forward through billions of years of planetary evolution. The hunt for Planet 9 has also revealed the collaborative nature of modern science, where teams around the world share data, compare results, and build upon each other's discoveries, even while competing for the ultimate prize. It shows how statistical analysis can transform astronomical observations into mathematical certainty, and how indirect evidence can be just as compelling as direct detection. Perhaps most remarkably, the search has demonstrated that major discoveries about our own solar system are still possible. In an age when Mars rovers analyze alien rocks and space telescopes peer into the earliest moments of cosmic history, we've learned that profound mysteries still lurk in our own cosmic backyard. The outer solar system remains largely unexplored territory where new worlds await discovery. The next decade promises to resolve the Planet 9 mystery one way or another. Advanced telescopes, artificial intelligence algorithms, and revolutionary detection techniques are converging to create capabilities that will either find our hidden ninth planet or prove definitively that it doesn't exist. We stand at the threshold of answering one of the most compelling questions in planetary science. But regardless of whether Planet 9 is ultimately found or ruled out, the search has already transformed our understanding of how planetary systems evolve and revealed that our solar system is far stranger and more dynamic than we ever imagined. What other cosmic secrets are hiding in the darkness, waiting for the next generation of planet hunters to uncover them? If you're fascinated by the cosmic detective work that's reshaping our understanding of the solar system, subscribe for more astronomical mysteries and hit that notification bell so you never miss the latest discoveries from the final frontier.